Here we pick up with equilibrium. And if you remember last time we talked about equilibrium and the idea that equilibrium, and when we reach chemical equilibrium, what we're referring to is, again, the rates of the reaction. So because it's a reversible reaction, at some point the forward direction and the reverse direction will basically equal each other. And when that happens, that again is when chemical equilibrium really has been sort of met. And we saw last time a couple of things. We saw the idea of Q. Q is what is referred to as the reaction quotient. The reaction quotient is used in a couple of situations, one of which we've already sort of seen, which is a sort of straight Q type problem where you're trying to figure out whether or not, the reaction is at equilibrium. The way that we calculate Q is the exact same way that we calculate the equilibrium constant. The only difference is you're sort of using perhaps like initial concentrations, or you're not sure you're at equilibrium type concentrations. So when we use that Q, we can compare it to the Kc value or the K value. And if Q is less than the K value, that means that you're not at equilibrium, and you would need to go towards the product side to reach equilibrium or make more products to do that. If Q is greater than the K value, that also means that you're not at equilibrium. And in order to reach equilibrium, you need to head towards the reactant side. Now, if Q does equal K in that case, then that would mean that you are at equilibrium in that particular case. We also then talked about basically how to solve equilibrium problems. So if we are given the initial, say, concentrations, we could also be given for perhaps the initial pressures if we're dealing with gases. How can we get to sort of the equilibrium concentrations or the equilibrium sort of pressures? And as we talked about, pretty much the method that we use here is the big calculation of really the semester is doing ice tables. So we do these ice tables, and ice tables basically represents I for initial, C for change, and E for equilibrium. The initial, again, is typically in these type of problems at this point, the initial concentration and molarity. It could also be pressure. And this is the part where I was talking about also earlier on in an earlier lecture that, if you are given pressures and you need to do an ice table like this, you need to make sure that those pressures are in atmospheres when you do the calculation. So if you happen to be given pressures and maybe they're in some type of other unit like torr, millimeters of mercury, something like that, and you then need to use those values in an ice table, you do need to convert them to atmospheres, do the conversion, and then convert them back to whatever unit you're looking for. So that was the point earlier on in sort of our lecture here about equilibrium that I had mentioned. You want to make sure things are in atmospheres, and this is really the place where you want to make sure of that. You want to make sure that when you're doing an ice table, if you happen to be dealing with pressures, and by the way, it works the exact same way as concentration. Everything's pretty much done the exact same way, but we want to make sure that those things are in atmospheres. So we have our initial, and usually if you are not given anything on the product side, it's pretty safe to assume that you are starting with zero. So probably 9 times out of 10, when you do an ice table, your product side there is going to be zero. The change is also that assumption, because we are assuming we have no products, that this reaction would have to head towards the product side in this case. Basically, that forward direction is going to start because you have no products. So you got to start making some products before the reverse direction could even think about happening. So it's a pretty safe bet in most sort of problems. And again, not 100% of the time, but in most problems that the change part, we represent that by minuses on the reactant side. And that's basically implying that we're going to be decreasing our reactant. Positive on the product side, which basically means, we're going to be like increasing our products. And we also, very important in terms of the change part, is actually the coefficients. And really the coefficients here, when you put them in, takes care of all the stoichiometry for you. So basically all that mole to mole relationship and stuff like that. You need to make sure you do that. And that's why when this example that we finished up on last time, we had a 1 was the coefficient, and obviously it's just minus x, which is basically 1x. We had a coefficient of 2, and that is why that is, again, plus 2x. So that is extremely important as well. If you don't put those numbers in, you're going to get the wrong answer. It's not going to actually work out correctly because you don't have really the right mole to mole relationship. Once we do that, the goal here is really to solve for x. X represents that change. X will also allow us to really figure out, what is the equilibrium concentrations of everybody, because that's sort of our unknown here on both of these guys. In this particular case, we would go into the equilibrium expression, and then basically this is where the math kicks in most of these problems. We got to do some math here to solve it. So in this case, we had to multiply to the other side, and we basically got our quadratic sort of equation and formula that we had to use in this particular case to solve this problem. This is the case area where you want to be really careful. You want to make sure, you're very careful in terms of the calculation, because there's a lot of places, obviously, as you're sort of distributing everything, where things can go kind of wrong for you and stuff like that. When we do finally get our quadratic, which was right here in the middle, it looks like, we had our A, B, and C value, and that went into our quadratic formula here. And as we talked about last time, as you may be familiar with, obviously when you use that, you will end up with two different x values. And we did as well up here, as you can see. And a reminder that when you do get those two x values, you actually can get pretty much every combination you could think of. You could get two positive numbers. You could get a positive negative number. You could even get two negative numbers, and sometimes is okay. So you can sort of get, any combination of numbers out for the x. But what will always happen and should always happen in these type of problems is when you take one of those x values and kind of put it back into the equilibrium spot here, for example, this 2x, if I took that 2x times that negative number that I had for my x value, that will give me a negative concentration. And clearly you can't have a negative concentration. So one of the answers from the quadratic will not make sense. And that's obviously going to be the incorrect one, while the other answer there would make sense. And that's what you would put in to the equilibrium line. And that would get you your equilibrium concentrations in this case, like what we did here. Now, as we also talked about at the end there, you can actually then go back into the equilibrium expression and put in the correct values there into there. And so that guy would go on top, that guy would go on the bottom. And really what you should end up with is an equilibrium constant value that pretty much matches the one that was given to you in the problem. Is it going to match perfectly and be exactly the same number? The answer is really probably not, but it should be definitely, with rounding, pretty darn close to the value that's given to you. You might even hit the value pretty close, or may even hit the value, but a lot of times it won't be. But, it should be pretty darn close to that, like here I got like 7.01 and the value given to us was 7. So that's obviously very close. And that's a good way to sort of check yourself if you have the time to do so, because like I said, there's those little spots along the way when you're doing the distribution, the factoring, the foiling, or whatever you want to call it, that, there's areas where you could potentially make a mistake. And, this is a good way to check to make sure you didn't. So like I said, maybe last time, if you put those numbers back in, maybe even like I did incorrectly, but if you put the right numbers in back into this K value here, and you got like a K value of like 200, and the problem gave you one of 7, then clearly something probably went wrong with your math. You would obviously want to go back and sort of check it out. Any questions on that stuff that we talked about last time? Okay, so now that we kind of did one together, why don't you take a stab at it here and see what you come up with? So in this case, we have a mixture of 0.5 moles of H2, 0.5 moles of I2 were placed in a whatever liter flask that was, a 1 liter flask, and it reaches equilibrium, and the constant is 54.3. What is all the equilibrium concentrations? So take several minutes here, work through it. Again, ice table, see what you come up with. And then obviously we will go over it and make sure, hopefully, everybody's got the same answer. So take a little bit and we'll talk about it here in just a second. one, see how you're doing. All right, so obviously we're going to be doing an ice table here since we're given initial concentrations and we're trying to find equilibrium concentrations. And actually in this particular case, we're actually not necessarily given directly the concentrations here, but we are given the moles and the liters. So that's going to allow us to really find the concentrations of everybody here. And in this particular case, it's pretty simple since we have 1 liter for everybody. The concentration of H2 in this case would be 0.5 moles divided by 1 liter. And I could do that math, I think. It's going to still be 0.5 molar. For our I2, going to pretty much be the same here. We're going to get 0.5 moles per liter, 1 liter. And that will also give us 0.5 molar. Any questions on that part of it there? All right, so because we have our initial concentrations and we are obviously looking for our equilibrium concentrations, that is your classic pretty much ice table type problem. So let us take a look at that. So we'll set up our ice table here. Actually, I'll write it in myself because I'm not sure I like the sizing there. We'll go with this. There we go. All right. We also obviously can write our equilibrium expression, which just like we've talked about a couple of times already in this chapter here, we're going to go products, again, making sure we use the coefficient there for the exponent divided by our H2 and our I2. And that is going to equal, that is our 54.3 number. So since we calculated the initial concentrations here, that's going to be 0.5 molar. That will also be 0.5 molar. And again, since there was no mention really of our product here, we can safely assume that it's going to probably be 0. In addition, because we pretty much do not have any products there sort of given up to us to start with, we could also probably safely assume that this reaction is probably going to head towards the product side. Again here, because we have no products, this is a reversible reaction, kind of like those earlier graphs we saw where you're like at time 0, there's like no products, but we do have some reactants. We would expect those reactants to start decreasing and in that process start increasing our product supply. And again, that's why we could assume here that probably the forward direction is pretty much what is happening here. Why is that important? Well, that's important really for the change part. So we can safely assume that we're going to be decreasing our reactants and increasing our products here. So this is going to be our minus x, and our plus 2x. Again, in addition to using it to square our equilibrium, we need to also have it here as well. So that's really important. Coming through here, we're going to bring everybody down. That's going to give us 0.5 minus x, 0.5 minus x, and 2x. Any questions on the ice table, how it got set up, or anything like that? I can answer for you. At this point, like we talked about last time, we want to basically plug these guys into our expression. So we're going to take everybody on the equilibrium line and basically just stick it into that expression. And that would get us that, if I can start writing there. That will give us our 2x. And again, it would be squared divided by our 0.5 minus x times our 0.5 minus x. And again, that would equal 54.3. At this point, we want to mathematically, obviously, solve for x. We also want to think about, is there a better way? So you might have started factoring and doing all that good stuff and headed towards the quadratic formula, but you do want to look at what you're dealing with. And hopefully you kind of recognize that it is a perfect square on both sides. You literally can take the square root of this side any square root of that side. And that's probably going to make it much, much easier to solve for. And if we did that, that would leave us 2x there up on top. That obviously would leave us one of those guys on the bottom. And also important, a thing, you know, I personally sometimes forget to do, you got to make sure you also take the square root of the 54.3 on the other side. And that's going to give you something like 7.369. This obviously is a little bit easier here to solve. We obviously would multiply this guy to the other side. And when we do that, that will get us 2x is equal to 3.6845 minus 7.369x. We're going to combine our x's to the other side. That's going to give us basically 9.369x is equal to 3.6845. Dividing that 9 to the other side, going to end up getting us, obviously not just a 9, but 9.369 would be good as well. That's going to give us 0.393 as our x value. Any questions on that math there? So the importance of that x value is that x value here is this x value here. It's that x value there, and it's this x value here. So that really is all that we need to sort of finish up and figure out our equilibrium concentrations. That means that the H2 concentration in this case will actually equal the I2 concentration, and they both are 0.5 minus x, which means it is 0.5 minus 0.393. And let me see here. Yeah, if you went quadratic as well, you should end up with really the same answer. So I would just double check to make sure, because let's see here, you should end up with, in terms of the concentrations here, would be 0.107. That's a bad zero. 1.107 molar for each of those guys. And if we did our HI, you get 2x, and that should be 2 times 0.393. And you'll end up with 0.786 molar here. So those would be our equilibrium concentrations. And again, we could check it to make sure, you know, that we hopefully didn't mess up anywhere. And if you did that, you end up with basically 53.96, which is basically 54, which is pretty darn close to, obviously, the K value. Now, I see your question. I would think that you should pretty much end up with the same x value as you went through the quadratic. Should kind of come out the same. So I'll just double check everything to make sure that you did come out with the same here. And obviously you can see our numbers there are pretty much dead on that 54.3. So just double check that calculation to make sure. Okay, you did get the same value. Oh, you got the same value of that? Okay, perfect, yeah. Okay, so yeah, okay, so I'm seeing there everybody did get at least the same x value for the quadratic, and you definitely should get the same x value for the quadratic formula. You know, it should result in the same concentrations, obviously. Okay. So just double check the math. Again, it really should come out pretty much the same in terms of the x values on both of those. Again, you do have the option. You obviously could do the quadratic formula in all these sort of situations. And you know, if you go sort of the quadratic format route, you should really end up with sort of the same x value. Now, remind you, if you do go to quadratic formula, if you did go into quadratic formula, you may slightly get a different x value because there's a lot more places, obviously, in this case for you to do some rounding. And that little bit of rounding might be the slight difference that you might be seeing in your calculation and stuff like that. So that also could maybe account for the slight difference that you might get is kind of where you rounded, because obviously as you distribute and all that, you're going to do a little bit different rounding with the quadratic formula, but you definitely should get pretty much the same number or pretty close to the same number, you know, for the x values. Yes, to answer your other question, the 54.3 was the sort of k value that was given to us in the problem. And obviously in these type of problems, when you're trying to find equilibrium concentrations or something like that, you would usually be given obviously the k value. Otherwise, you would have no way to really you know, sort of be able to check it and stuff like that. Yeah. So yeah, definitely you could do the quadratic. You definitely should end up with really about the same x value. But I'll be honest with you, you know, if you do a little bit slightly different rounding, as always in a calculation, you may get a slightly different number. And obviously there's a lot more calculation steps in that quadratic, which, you know, you might round a little bit differently. But, you know, for example, I got 0.393. If you did the quadratic, you shouldn't end up with like, you know, 2 point something or 6 point something or 0.6 something for your x value. You should get pretty close to it. Other questions on that? Okay, so here again, you know, when you're doing these sort of problems, if you like the quadratic, again, like I said, you could always go into it, but you might want to think about other ways to solve them sometimes. But again, the quadratic might be the only proper way to sort of solve it. So let's take a look at another one here and see how we did. So we're going to basically be looking at the same reaction, but in this case, we have 0.00623 molar H2. I2 is 0.00414, and HI is 0.0224. In this case, we want to know again what will be the equilibrium concentrations for everybody here, same K value. And again, the slight difference is we actually have some starting amounts of everybody here. So why don't you take a few minutes here, just like the last one, work through it, and then we'll go through it and stuff like that. Approach sort of this type of equilibrium problem. First off, a little bit different is in this particular case, they did give you the starting amounts of H2, I2, and HI. So that implies, you know, you got this sort of reaction going. You got a little bit of everybody going. So that should beg the question of, you know, are you at equilibrium? And the reason for that, again, is you have pretty much everybody there. The answer is probably going to be no, you're not at equilibrium. Otherwise, again, probably wouldn't be much of a question for you to answer. But this is the other situation where you should use something like Q. So remember earlier we used Q to figure out, you know, are we at equilibrium? And if we're not at equilibrium, which way we need to go to reach equilibrium? Here we probably have a pretty good guess that we're not at equilibrium, but we might want to know which way we need to go to reach equilibrium in this particular case. Remember that if we were to calculate Q, it is calculated the exact same way as we calculate K, which means we take products over reactants. And here we would put in all of our information for Q. So HI was 0.0224. Again, we would square it. We also have our 0.00623 and our 0.00414 in this case. Now, that gives us a Q value of 19.5. Remember that when we do Q, we basically are going to compare it to the K value that was given to us. And what we see in this particular case is Q is less than K. So it did pretty much verify the fact that we're not at equilibrium because, again, not much of a problem if it was at equilibrium. You just basically stop at that point. But more importantly, what it tells us is in order to reach equilibrium, we need to go to the right. We need to basically go towards the products here. So why would that be important? Well, that's important if you think about your ice table, right? Now, going to products makes us know for sure when we do the minuses and the pluses, we're kind of doing it right, in that sense. If we calculated this and it was the opposite, like, hey, you got to go towards reactants, what that would mean is, basically you'd be kind of going minuses here and like pluses this way, right? So it would sort of be opposite of that because you basically would be heading, in this direction. And that's obviously not the case here. And probably, like I said earlier, in most cases, probably not going to be the case, but it potentially could occur. So you do want to kind of, calculate it and make sure it's not the case, in a problem like this. Any questions on that there? So this is sort of the second place where we will sometimes use Q. And you might be asking yourself, well, we calculated Q here. Why did we not calculate Q like in the previous problem? And the answer would be, or the previous two problems, I guess. The answer would be you really couldn't, right? Because in the previous couple of problems that we did, we were not given anything in terms of the products, in terms of their concentrations, which means you have really no ability at all to calculate Q. And that's why we were able to make sort of that assumption that the reactions previously are definitely going to the product side. But here, you probably will be safe, but you can't 100% in this case make that assumption without technically calculating Q and making sure that, A, you're probably not going to be out of equilibrium because it wouldn't be much of a problem, but B, you need to really do it to verify sort of that change part of your table and which way it's actually going. Any questions on sort of that part of it there? Okay, so now that we sort of safely assume that it is going the way we would expect it to go, now we get into the actual ice table part of it. So here we're going to set up our ice table the same way. We got our H2, we got our I2, and we got our 2HI. We obviously will have the same expression as we had in the previous problems. This is the same reaction. And it has the same K value as well, which is going to be our 54.3. So initially here, it looks like it was 0.00623 molar, 0.00414 molar. And again, here we actually do have a value on this side. By doing the Q, we did verify that it's going to be heading in this direction, which means we're going to do minuses on the left here. So this would be minus X, this would be minus X, and again, this would be plus 2X because of the coefficient that we got going on there. That means when we reach equilibrium, this is 0.00623 minus X. This is 0.00414 minus X. This is 0.0224, and it is plus 2x. So that's also something sometimes people will mess up on in a problem like this because they have a number to start with. They're so used to a number to start with that's minus after that they will sometimes do the minus on the right-hand side as well. So again, that's something you want to watch out for. Just like we did before, we're going to put this into our equilibrium expression, and that is going to be products, which is this guy. On top, we're also going to square them. We're going to then put it for this guy here. And all that's going to equal our 54.3. All right, well, this one, not a perfect square. This one, you got to go the quadratic root, which means here we go with some factor fun here, right? FOIL method, whatever you want to call that. We'll start with, let's do the top. So I'm just going to kind of do the top first, and then I'll do the bottom, and then we'll kind of put it back together. So if you look at the top, that's basically 0.0224 plus 2x times 0.0224 plus 2x. And if we put all that together, we're going to do some factoring. And if you factor it out correctly and combine everything there up on top, you end up with something like 5.02 times 10 to the minus 4 plus 8.96 times 10 to the minus 2x plus 4x squared. And again, that is this, right, times that, and then back this way and this way. So when you do the 0.0224 times 0.0224, that's where this number comes from. You take 0.0224 times 2x plus another 0.0224 times 2x, and you add it together. That's where this number comes from. And then obviously 2x times 2x gives you that number at that point. So individually, what you get, just to show you, I guess, the numbers there, you end up with, when you do sort of this to the 2x, you end up with this number, 4.48 times 10 to the minus 2x, and it's going to be plus 4.48 times 10 to the minus 2x. And that is where this middle number comes from. So by factoring that out. So that's the only part I didn't kind of show there. So we're then going to do the bottom guy. And again, we're going to multiply the bottom guys together here and see what we come up with. And if we do, again, the bottom guys, 0.00623 minus x times 0.00414 minus x. Same sort of move there. We're going to take the 0.00623 times the 0.00414, and I believe we end up with 2.58 times 10 to the minus 5. We then will do our middle section there, which is 0.00623x minus 0.00414x, and then we got plus x squared. Kind of cleaning up the middle guy there gets us 2.58 times 10 to the minus 5 minus 1.04 times 10 to the minus 2, and that's going to be x, I believe, plus x squared. Any questions on those factoring type of moves? All right, at this point, I'm going to kind of put both of those sort of equations back together and the right orientations and continue on. So up on top, we had basically this after we kind of factored out everything. And on the bottom, we ended up with this equation. And again, that all equaled the 54.3. We're then going to obviously take our bottom all the way to the other side there. And that's going to give us 5.02 times 10 to the minus 4 plus 8.96 times 10 to the minus 2 plus 4x squared. And that is going to equal, when we multiply that to the other side, 54.3x squared minus 5.63 times 10 to the minus 1x and plus 1.40 times 10 to the minus 3. And again, that's just multiplying everything on the bottom to the other side. Any questions on that so far? Well, we're almost there. We're pretty much, in most cases, most people keep the x squared value positive, which means in that case, I'm going to take everybody's on the left-hand side and kind of subtract it over to the other side and combine. And when I do that, that leaves us finally with a very scary looking formula here. That's going to give us 50.3 x squared minus 6.53 times 10 to the minus 1x plus 8.98 times 10 to the minus 4 is equal to 0 at this point, we now have our actual quadratic formula there. Any questions up to that point? All right, well, this is now going to be obviously our A value there. That's going to be our B value. That would be our C value. So going into our quadratic, X is going to equal, again, minus B. So in this case, that would be 6.53 times 10 to the minus 1, plus or minus the square root of our B squared minus 4AC. And if we kind of clean up all that numbers inside, you end up with something like 2.46 times 10 to the minus 1, which if you do a little square root action on that, that is 4.96 times 10 to the minus 1. And that's going to be all divided by 2 times A, which on the bottom would get you about 100.6, I believe. At this point, we now have everything we need to get our two X values. So we'll do the positive here first. So the 6.53 to the minus 1 plus the 4.96 to the minus 1 divided by our 100.6, looking like we end up with, we got there 0.0, we'll call it 0.0114 R. If we come through and do the subtraction, so 6.53 to the negative 1 minus 4.96 to the negative 1 divided by 100.6, and that's going to give us 0.00156 as our two X values. Any questions up until that point there? All right, so we obviously got two positive values here. We want to kind of, see if one of them makes sense and one of them maybe doesn't make sense. So what we really want to do is, and I'm just going to kind of, maybe I can do it down here. I'm just going to take that equilibrium line from our ice table. And if you remember for H2, it was 0.00623 minus X. For I2, it was 0.00414 minus X. And for HI, or 2HI, it was 224 plus 2X. So looking at this, we could kind of see that obviously this number here, if we were to put it back into say here, is going to give us a negative number. So this number here would not be the right number, as it is really too large, right? So that is too large of a number for really our H2 and I2. That means this guy here should be our right number. So let's see. We'll put that in. So H2 then would equal 0.00623 minus 0.00156. And that gets us, if I didn't clear my calculator here, gives us something like 4.67 times 10 to the minus 3, and it would be molar since it is a concentration, right? Our I2 would end up at 0.00414 minus 0.00156, and that gets us 2.58 to the minus 3. And lastly, our HI here would be our initial, which was 0.0224 plus 2 times our X value, which is 0.00156. And that ends up getting us, if I punched a number in right, that would probably help. 2 times 0.00156, or we'll call it 2.55 to the minus 2 molar as well. Any questions on kind of any of those steps, where any of the numbers came from? you could clearly see, hopefully, that you got to be really careful here, as there is a lot of places in the math part that it could go really bad for you if you kind of mess up on any part of it. Again, if you put in our values back into our K expression, you get something like 54.1-ish, I think. So that's pretty close in terms of checking as well. Any questions on any of those steps there? And, you know, if the math part here is difficult for you, or the hard part, I would do it kind of like what I just did. Just take it one piece at a time and then kind of put it back together, and just do it that way, rather than, you know, kind of putting it all together, broken out all the numbers and stuff like that. So sometimes easier just to kind of go, okay, like I did the top part first, get that equation, do the bottom part, get that equation, put them back together, and then kind of continue on in that point. Any questions on any of that one there? All right, so if your calculator hasn't exploded yet, let's try one more here. So give this one a go here. We have N2 plus 3H2 gets you 2NH3. And again, in this case, we're actually starting with pressures, and we're given a Kp value. So as I mentioned before, you could do ice tables and pressures just as good as you could do it in concentration or molarity. Again, the pressures do need to be in atmospheres, which they are in this problem. And again, you would approach it the exact same way as the previous examples we did. So give it a go, and we'll talk about it here in a few minutes, but work it the same way. It's just pressures instead of concentrations. Okay, let's take a look here and see how you're doing on this particular one. So again, in this case, we're given the Kp, and we're also given some pressures. So as I mentioned earlier, pretty much you want to approach it the exact same way as if you were dealing with molarity and the Kc value. Again, the one sort of thing that, as I mentioned a couple of times already, that you do want to just make sure of is, again, that your pressures are in atmospheres before they go into the ice table. And if they are not in atmospheres, make sure you do convert them. And if you need to convert it to some other unit after you solve the problem, then that's how you should kind of do these problems. So again, sometimes people are given problems with pressures in, say, torr, and they're asked to give the answer in torr, so they feel like, okay, I could just go into the ice table in torr. That kind of makes sense, and you won't get the right answer. So you do have to, again, for the ice table part, make sure you got that thing in atmospheres. So let's take a look at this here. And so since we're given really just the atmospheres there for our starting guys, we are okay in terms of going into our ice table. So this is we got there. I'll just go over here. N2 plus some 3H2 going over to 2NH3. We could write our Kp for this. Remember, since it is a Kp value, it's really the partial pressure squared of NH3 divided by the partial pressure of N2 and the partial pressure cubed of, make that an H2. And that would equal our 4.31 times 10 to the minus 4. So we do the same thing, right? We use our coefficients here as our exponents. Again, not really concentrations, but partial pressures. Putting in initially our pressures, we had 0.862 atmospheres there for our nitrogen, 0.373 for our hydrogen. And again, since we were not given any information about our products, that would zero out. Change going to be minus x, minus 3x, and plus 2x, again, on the assumption that this reaction really is sort of heading in this direction. Since we were not given any products, that is usually a fairly safe assumption. At equilibrium here, we would end up with 0.862 minus x, 0.373 minus 3x, and 2x. Any questions on sort of the ice table, how to set it up, or any of that there that I could answer for you? So just like we've sort of done before, we're going to put these guys into our equilibrium expression here. And that would get us that we have 2x squared up on top. divided by our reactance, which would be 0.862 minus x, and 0.373 minus 3x. And we also need to cube that guy there. And that's going to equal our Kp value of 4.31 times 10 to the minus 4. At this point, we need to solve for x. So clearly the right answer here is, skip it, go to the next problem is probably the best move, I think, in this case. That looks pretty scary and a lot of math that, you probably don't want to do anyway. So no, you probably shouldn't skip it, but we should solve it. So let's think about maybe an alternative approach that might work okay in this situation. And that alternative approach revolves around the actual K value there. When we look at this K value, that is 4.3 times 10 to the minus 4. That is considered a small value of K. And if you remember, when we talked about K values, a small value of K means that when we reach equilibrium, we would mainly expect to be their reactants, right? Present. So what does that really mean in a situation like that? Well, it means that when we reach equilibrium, these are pretty much the guys we expect to be there. And what that means is the actual change part in that case shouldn't be too big. So it should be relatively small because there's not going to be a lot of X sort of transferring over to the other side to make products. There is going to be some, obviously, but there's not going to be a lot kind of going to the other side to make the products. So in a situation like this, where you have sort of a problem you don't want to solve like a traditional way, but really more so you have a problem where you have a K value that is small. You could actually make an assumption and you could assume that X is equal to 0. It's pretty much negligible. There's not going to be that much change occurring. And really, we would expect kind of our initial and our final to be pretty close to each other when it's all said and done, because there's not going to be that much change occurring. So we could assume X is equal to 0, but you cannot get carried away and go, cool, I'm just going to, cancel out all the X's. You would have nothing to solve for at that point. So the only X's that we typically will assume that's equal to 0 are X's that we're going to kind of subtract from a number. So like this X and this X over here. Everybody else, the X on top is not going to be 0. Because just logically speaking, if you zeroed out everybody, you got nothing to solve for. So, but the real reason is in relationship to where the product started with in terms of its pressure in this case. Whatever it gains, because he started at 0, is going to be pretty significant for it. The difference, though, is in terms of our reactants, where they started with and where they end up with, the change is going to be relatively super small, almost negligible, and that's why we zero out those guys that we subtract from. But anybody that sort of starts at 0, whatever you get is a pretty big deal, right? So like if you had $0, you got $1, that's good, right? You got like 50 cents, that's good as well. So the change that occurs when you start with nothing to just getting anything is relatively big, not really negligible. But if you started with say 0.373 and then maybe you only lost 0.002 or something like that, that's not going to be a very big amount coming off of our original sort of pressure and stuff like that. So when we do that, and by the way, any questions on the assumption there? When we do that, obviously will make the math part pretty much a lot easier. That would reduce this down to 2x squared. Again, our guy on the bottom will become 0.862 because we zeroed out that x. By zeroing out the x on the other guy, it takes care of the 3x part, and we end up with 0.373, and that equals our 4.31 times 10 to the minus 4. At this point, I'm assuming, like most people here, you would much rather solve this equation than the previous one. So we will do that. And we're going to do that by really just multiplying everybody on the bottom to the other side. And that will get us 4x squared is equal to 4.31 to the minus 4 times 0.862 and times 0.373 gets us something like 1.386 times 10 to the minus 4. We're going to divide it by 4 to the other side, also do a little square root action on it while we're there. And so let's just make sure here I got the right number. Hang on a sec. There we go. So I think I might have punched one in wrong. Just make sure here I did not do that correctly. That's because I forgot an important part. We still need to cube it here. So also, see, even I make a mistake occasionally. So you want to make sure you watch out for those things. Again, you need to make sure that you do cube the value here because of the 3 that was there. And that would obviously make the difference there. So let me do that correctly. See, there's these little things that you do want to make sure you watch out for, because even somebody like me can do it as well, kind of mess up there a little bit. That gives us a better number. I think that's going to get us, hopefully, a 1.928 times 10 to the minus 5. Now we're going to divide it by 4. We're also going to now do a little square root action, and hopefully we end up with a much better number there. And that's going to be an x value of 2.2 times 10 to the minus 3 in this particular case. Any questions on that there? So again, important as well. And again, I overlooked it there. We do need to cube it because of the cube that was there. Any questions on that so far? Now, can you do this and just do it and not worry about it being correct or wrong or anything like that? Well, the good news and bad news is when you do an assumption such as this, you do have to do a check of your assumption. Yeah, so you got to check your assumption there that x is equal to 0. How do we check it? There's a few different ways, but we'll use in this class, and a lot of people will use what's sometimes referred to as the 5% rule. And the 5% rule basically means once you get your x value, you take that x value, which would be 2.2 times 10 to the minus 3, and then you divide it by what you were going to subtract it from. So in the case of our N2, it was 0.862, and we would times it by 100. And when we do that, we end up with like 0.25%. Excuse me. And obviously 0.25% is less than 5. And what that means is our assumption is good. We checked it. We're happy. You could actually do it for both if you like. So you could actually put it into here as well and see what you come up with. And to be honest with you, in most cases, if one of the checks work, probably the other one is going to be good to go as well. So we'll put that in there as well. Also kind of multiplying by the 3 times it by 100. And like I said, usually if one's good, the other one will be good as well. And we can see it also is less than 5%. So as long as you check it, and you should always check it because it will not always be good. But as long as it's less than 5% or 5% or less, then you technically can say pretty much that change was negligible. It's okay to zero it out, and you can use that as your x value. Question on that? Now, if it's over 5%, that is kind of bad news, because then you would have to, kind of go back up to here and actually solve it some other way. The good news for us is that other way would most likely be the quadratic formula. It would be sort of the hardest thing that you would have to do. So if you do have a problem like this, you can make the assumption. By the way, you can, if you like the quadratic, like I said before, continue to use the quadratic and not do the assumption at all. Again, it should get you to the same sort of outcome when it's all said and done. Now we're not done with the problem, so let's actually sort of finish the problem here. Now that we checked our assumption and it's all good in that sense, let us then put our x values back in. And that means that we have for our N2, and again, this is pressure, which means technically this is atmospheres happening here. So our partial pressure there of, that was N2, I believe, is 0.862 minus 2.2 times 10 to the minus 3, which means we end up with 0.862 minus 2.2 to the minus 3. We got there, we'll call it 860. And this would be atmospheres. We would do our partial pressure of our H2, which in this case is 0.373 minus 3 times X. And 0.373 minus 3 times the 2.2 to the minus 3 value gets us 0.366. Again, they would be atmospheres. And we'll do our partial pressure of NH3 over here, which would be 2 times X, 2.2 times 10 to the minus 3. And that's going to get us an X value of 4.40 times 10 to the minus 3. Also going to have atmospheres there as well. Any questions on that calculation, why we did anything, the assumption part of it that I can answer for you? Okay, so in this particular case, a couple of things just to kind of wrap up this sort of talk here. Obviously, again, you could do the assumption, and if it's not a good assumption, you again has to go back and do some type of quadratic. Why did we not do the assumption on the previous examples we did? Well, the answer is if you go back to the previous examples that we did, I believe the K value for the first one we did was 7. So that is considered a large value of K, which means you cannot do the assumption in that case. We also had K values of 54.3, which is definitely a large value of K. Also means you cannot do the assumptions in that particular case as well. So that's why we did not apply the assumptions in the earlier examples. You could only apply it in a one where you have a small K value, kind of like a negative exponent. But you do absolutely need to check it because I can guarantee you it will not always work. So if it doesn't work, again, like I said, you got to go back and kind of do the quadratic. Any questions on ice tables, equilibrium, how to calculate equilibrium, pressures or concentrations or anything like that?
Can you only do the assumption for pressure? Can you do that for concentration too?
You absolutely can. So this, again, pretty much pressure and concentrations, again, it works the same way in terms of the ice table. It's not really based on whether it's pressures or concentration. The assumption is really based on the K value that you have here. So as long as this K value, and really, even though it's a KP value in one case versus a KC value in another case, as we'll see as we go through all these different chapters, there's like KP, KC, KA, B, all these different K values. But ultimately, they're all really the same thing in the sense of their equilibrium constant values, their products over reactants. So as long as whatever K value you're given is relatively small, it's basically going to mean the same in the sense of when you reach equilibrium, you should mainly have reactants. And because of that, the change part should be relatively small that's going to occur. And that's why we can make the assumption. And again, you could do it for molarity or pressures, but it's really more based on the actual value of K. Other questions on that? Okay. One last thing to sort of tie up here, the equilibrium is, again, for us, those are pretty much the three different ways that you would be asked to solve one of these problems. And the three kind of ways that we talked about was You're welcome. Three different ways that we talked about was using the quadratic formula. You'll have a situation where you might have a perfect square on both sides, like we did in that particular one, or this situation here where you would do obviously the assumption. There is another way that sometimes people will solve these type of problems, but we're not going to ever do that in this class, and that is what's sometimes referred to as successive approximation. And successive approximation basically means that, for example, in this situation, the x value has got to be less than this number. So essentially, you kind of put an x value in there that's less than that, and then you solve for like this x. And if the number you put in equals the number that you get out, then you're done. But if it doesn't, then the number you get out, you put back in, and you keep kind of putting back in and getting a number and solving for x. And it could be 1 time, 2 times, 3 times. You're really crappy at it. It could be like 400 times, I guess. But you kind of keep going until the number you put in equals the number that you get out. And then, you actually solve for, the correct x value. So since that could go bad in a lot of situations, we will not do any type of successive approximation to solve these type of problems. But I tell you that in case you come across some type of material, sometimes books will do that. Sometimes like, kind of solution guides will do that approach and stuff like that. But we will definitely not do that. So those would be the 3 major ways we'll do the type of problems in here in terms of equilibrium, which again is basically a perfect square, quadratic formula, or you can make the assumption. Any other questions on that there? Okay. So we're pretty much almost done here with this chapter and equilibrium. We have one more thing to talk about, which is Le Chatelier's principle. We'll obviously talk about that next time. And that will wrap up pretty much equilibrium for us.